Welcome to episode number 133, in which we're going to explore IPsets. What are they? What are we going to do with them? Like how it all works. We're also going to talk about like when you would use IPsets, and then we're going to introduce a new idea that is actually recently landed in Cilium. That's called Cilium slider sets, and we're going to talk about how those things kind of interact, like how they are related and how they're not related, and like how we can use those things. So that'll be the goal of today, is to get into IPsets and Cilium slider sets. That should be a lot of fun. But first, as usual, please let me know you're out there. If you're listening, it'd be awesome to see you in the chat. We'd love to know that you're there. Let's start first with our news. So there's some upcoming CFPs. The KubeCon NA CFP for Salt Lake City, Utah is coming right up. Definitely, if you're interested in putting in a talk, or if you want just some help, like assembling your talk, or you want to bounce that talk idea off of somebody, I'm always here for it. You can catch me anywhere at MAUILION, Maui Lion. You can also sign up for various KCDs, or Kubernetes Community Days. And if you go to cncf.io/KCDS, that's where you'll find all the information for the KCDs, including one that I'm actually really looking forward to in New York in May. That's Washington. Yes, there we go. May 22nd in New York. Looking forward to being at that one. Should be a lot of fun, but this is the full list. And if you'd like to sign up and do a talk or a presentation at one of the local KCDs, I'm sure they would love to have you. Lots of great stuff out there to go and do. In Cilium News, we of course have our newsletter. Let's take a look at that, see how that's looking. As always, you can sign up for this newsletter just by going to cilium.io/newsletter, entering your email address, and hitting subscribe. So we just went to Open Source Summit, and I actually had so much fun at the Open Source Summit. It was a total blast. I got to hang out with Mr. Bill Mulligan and quite a few of my coworkers at Isovalent, and just had a wonderful time. It's very much a community-based event, but it was a really good one. The technical, we've got Hello eBPF XDP based packet filter, which is neat because when you're using XDP to block traffic, you actually block that traffic before it leaves the network interface itself, which means you don't end up wasting a bunch of CPU cycles on dropping packets. So if you can actually get away with like designing a firewall that configures the XDP interface, you're able to actually drop that traffic early enough in the process that you don't really spend a lot of time in CPU handling that, which is pretty neat. There's KEISKU Gmon, eBPF tool for monitoring a Go routine. Seems interesting. Haven't explored those yet. We have a case study for WSO2. Neat. It's one of the open source users. Wow. Definitely worth checking that one out. That looks pretty awesome. We have a second workshop on eBPF and kernel extensions at SIGCOM Sydney in 2024. CFP is now open. We just saw an announcement from Cisco talking about Hypershield. And if you look at some of the details around that announcement, there's a lot of eBPF mentionings in there. And I think, it's super exciting to see like what we're going to be doing together, Cisco and Isovalent. I'm very excited for the future. Powered by eBPF technology, CubeSense pioneers the future of observability beyond agent-based tools, so another player in the eBPF observability space. Obviously, Cisco has completed the acquisition of Isovalent. Many of my fellow Isonauts are kind of going through the whole onboarding process, as am I this week. Lots of stuff happening there. Oh, neat. There's a whole AFL Levering 50 networking secrets exploring eBPF, CNI, and service mesh. That looks pretty good. Tetragon on AKS, dual stack on AKS with Cilium. That means using IPv4 and IPv6 inside of your cluster. You can actually do any combination thereof too. It's kind of neat. You could actually have dual stack be one thing or another. Welcome. How you doing, Richard? Welcome. And from West Palm Beach, Florida. I mean, that sounds like a pretty nice place to be right at the moment. Some of the new events, we have an in-person meetup in London on April 23rd, talking about Kubernetes networking. Is that, no, it was like 3 days ago. Yeah, and then if ever you want to know about more events that are happening within the isovalent schema, or you can always come here and see kind of what we're going to be up to. So we're going to be at DevOps Day in Berlin, KubeHuddle in Toronto. We're going to be at FRNOG. I'm not sure what that one is, but that looks pretty interesting. DevOps Days in Berlin. I already said that, in Berlin. KCD Istanbul. The AWS Community Day in Turkey. Microsoft Build is coming up. That KCD in New York I was just mentioning. Container Day Security in Berlin. Lots of really great stuff coming up here, including Cisco Live. So tons of really great, exciting stuff. Really looking forward to kind of getting out there and doing those things. So that is the news for the day. Let's jump into the fun part. I'm actually curious how many people in the audience have ever heard of IPsets. So if you have heard of IPsets or used them in the past, definitely give me a thumbs up in the audience. And if you have not, or you could just say yes or something like that. And if you have not, then say no, because I'm curious about this, because it's actually a really interesting technology that has a specific set of use cases. And we're going to talk about those use cases and how we map them into things like Cilium network policy. And I think you're going to dig it. No answer so far. All right. So I'm going to say probably most people haven't heard of it. But let's talk about what it is. So let's say you were going to, actually, this is a great example. So this is an article that was written by Ken Volk, and they're doing a performance benchmark analysis of egress filtering on Linux. And the idea of this is to basically come up with ways to evaluate the performance of a variety of different technologies that can limit egress technology or egress packets on leaving a host. This has nothing to do with Kubernetes. This is just, I have a web server, or, like this is my, I don't know, it could be my Linux laptop, whatever it is, and I want to be able to limit the egress traffic leaving this particular host or this server for any number of reasons. How can I go about it? What are the different technologies that can do it? And then to really kind of talk about like how it actually works. There are a variety of different technologies that could be used. Today, we're going to be looking at this one here. We're going to be looking at IP tables, and then we're also going to be looking at Cilium network policy. And we're going to kind of like talk through like the different patterns for how this works. Because if you think about it, egress policy or even ingress policy, you might actually have very good reasons why you want to allow or disallow traffic from or to a given CIDR, right? So in this particular case, this IP tables rule that has been defined says I want to on traffic that is outputting, if the destination falls within this CIDR, 192.168.0.0/16, and the output interface is ETH0, I want to drop it. Right. And so the idea is that when traffic comes in, IP tables will actually look at that traffic, they'll look at the destination, determine if the destination is within that CIDR, and drop that traffic. And that's probably one of the more common uses of IP tables in general. I mean, it could actually also work the same way for traffic that's incoming, right? If I have traffic that's coming in and I want to know, like, if it's coming from my IP, for example, let's say I bring up an AWS instance in EC2, and I want to be able to limit the access to that EC2 instance to just the IP address that I'm coming from. There's actually a way to automatically do that with AWS network policy. But basically, in that model, I might say I want to limit the access to this particular EC2 instance, this public IP exposing this EC2 instance to the world, to just the IP address that's coming from my house, my cable router. And when I do that, this might look the other way around. I might say -A input, -S for source, and then the IP address of my machine, -I the interface that I'm actually referring to, and then I might want to say allow, and then set the default to drop, so that it would drop all of the traffic that's not established. But we'll get into that later. But let's say you wanted to actually, come up with a way to, let's say you have hundreds of IP addresses, or you have multiple subnets. How does IP tables scale in that particular regard? And let's talk a little bit about like how that's actually used and why you might want to do that, right? So like, for example, if you were going to, let's say you have an ad blocker, and one of the implementations of an ad blocker is to actually list the IP addresses of internet resources that are going to be used to host ads. So it would actually have things like CIDRs, where the servers where those ads are hosted are listed. You have a list of IP addresses. Sometimes those IP addresses are subnets, like a /24 or a /16, and sometimes those IP addresses are just single IP addresses with a /32 or something like that. But as you grow the list of IP addresses that you want to affect traffic for, that means that in IP tables, you would create one rule for each one of those IP addresses, or one rule for each one of those subnets. And that gets out of hand pretty quickly. And this article really gets into a great description of how that can actually get out of hand. Now, right in the beginning, it doesn't get out of hand very quickly, right? IP table scales pretty well up to about 1,000 rules. But when you start getting to 10,000 and 100,000, things get a little out of hand. And after that, IP tables can actually get to the point where like that's just too many rules for it to manage. And this is just throughput, right? This isn't actually even startup time. So if you look at things like there's a great here we go, setup time, right? So setup time for things like IP tables just by itself, the amount of time it takes to actually set IP tables up would be pretty long when it comes down to the configuration of this. And I think maybe I'm looking for a different graph. Because what's interesting here is that these are basically equivalent. Like it takes a little bit longer to set up IPset, and it should take a little bit less time. So that's confusing. Oh, here we go. This is latency. And the latency incurred with IP tables is significant, and we'll talk a little bit about why, because of convergence. But the latency config for IPset, which is IP tables using IPset, is less. This one here actually also shows it with CPU usage. IP tables with IPset is less. IP tables just by itself is more. So let's talk a little about what that means. So in this example that we described before, right, we have a rule set, and that rule set says that I have a given subnet and I want to match on it. Every new rule that I create will basically add to the number of rules that IP tables has to evaluate for every individual first packet that comes into the connection, that comes into the server or is trying to egress a server. And that can get to be quite a lot for the CPU to handle. Now, there's a way to shortcut this, right? And this is where we get into the fun stuff. One of the ways to shortcut this is using this technology called IPsets. So instead of creating one rule, because if you think about it, I have I have all the IP addresses for my ad blocks, right? I have like many IP addresses. I have many subnets for my ad block list that I want to block on, but I want to block on all of them. So the rule is effectively the same for all 1,000 rules that I've created. I can just only specify one destination per rule set. So what if instead of providing a destination, I provided a list? Right? And this is where IPset comes in, right? So I might say, for the 1,000 things I want to block out there in the world, instead of making 1,000 rules that describe each one of those 1,000 things, I'm going to add a list. I'm going to make a list of all of the things that I want to match. And I'm going to actually use that list as part of my IP tables rule. Now, this is much faster and it scales a lot better, right? Because it means that because the list is effectively an implementation of a hash table, which means it's very quick to look up and it scales linearly, and you can actually get away with one rule instead of many rules, which means that the hitting the number of IP tables rules that will be affected you have to hit like a much higher number before IP tables will be affected. And that's why when we look down here in the graphs, we can see IPset is not affected where IP tables is falling over, right? That's happening because when you add that many rules, that's just too many rules. IP tables like actually affects the throughput of traffic at that point. whereas IPset, an IP tables rule matching a list, does not, which is pretty neat stuff. Now, another thing you need to know about IP tables in general, and this will be like kind of probably one of the last things we talk about on the IP table side, because really this isn't about that. This is just about this whole pattern that we're describing. And I want to talk a little bit more about this pattern and then kind of move into like how all of this works inside of network policy and all of that stuff. So first, we have for you to, one more important thing to understand is that in IP tables, say you have those 1,000 rules that you've created, and you want to change one of those rules. Every time you change a rule, the setup time has to completely go through the entire process of setting up all of those rules again in the kernel, meaning that like there's a convergence time element to this as well. If you change one rule in IP tables, then you basically you're causing the kernel to completely reload all of the rule set. It's not atomic at all, which means that one rule change means that the entire set has to be reloaded. And as you grow the number of rules, and as you grow the number of times you change it, you actually can create a bit of a convergence problem in IP tables. However, that is not true for IP sets. So if you wanted to add or insert a new CIDR into that list of 1,000 IP addresses in that IP set, that is atomic. You can absolutely just add that to the hash. And you can remove from the hash. You can do all of that stuff dynamically. And it doesn't affect convergence time in IP tables because you're not changing the IP tables rule set. You're just changing something that it refers to. And that, my friends, is pretty damn cool. Because what that means is that you could actually scale IP tables to pretty significant numbers with things like IPset, which is neat. And when you take a step back and you look at the way that, like, say Cilium implements all of this stuff in eBPF, right? Well, the way that Cilium implements this stuff in eBPF is actually much more similar to this idea of a hash map, right? So if you had like a bunch of destination IP addresses that you wanted to drop traffic toward, or only specific IP addresses that you wanted to allow traffic from, then you would create that same list. And in Cilium, you would actually create what's called a CIDR list, right? Here's an example of a CIDR list, or of a CIDR or CIDR set. You create these things and you could create as many of them. You could have exceptions, et cetera, et cetera. All of those things are available to you in the network policy. And we would implement that as a hash map in eBPF. And if you wanted to change it, we would just be able to change the hash. We wouldn't have to actually rewrite the eBPF program, because in the eBPF program, we're saying if it matches this list, if the IP address is a part of the entries in this list, then we will drop it or allow it, depending on what the rule set was. Right. So it's actually kind of apples to apples in a way when you think about like using IP sets in IP tables allows you to greatly reduce the amount of CPU taken when adding lots and lots of rules or lots and lots of churn. All right. Interesting stuff. Let's get into some examples here. Oh, sorry. Boop. There we go. So let's jump into kind of playing with this and seeing how all of this works. Because I wanted to have like a practical example of this. So let's play with it a bit. For the first part, what we're going to do is we're going to actually set something like this up. And in this example, we're going to go ahead and we're going to create an egress policy that allows to a specific destination, but not to other destinations. All right, so let's jump into this a little bit. So there's to and from. Might be easier to do from, but let's take a look. So first, let's go ahead and create our Kubernetes cluster. So what I'm going to do first is I'm going to go ahead and create a Kubernetes cluster just using kind. And then I'm also going to install Cilium onto it. So we'll do kind create cluster config kind mno CNI, and I'll share that configuration with you while it's coming up. Cat kind mno CNI. So this is a configuration that will have one control plane node and 3 worker nodes. I'm using this flag here to disable the default CNI, and then I'm using these container D config patches to basically configure container D so that it uses my own local image cache for Docker Quay and GHCR. And the reason I do that is because it means that it takes way less time to do the install. All right, so now we'll do our Cilium install. If you want to do this, you can actually just grab the Cilium CLI from GitHub repository or from your own package manager. Cilium will do a bit of a, we'll do some interesting stuff. Like it will actually, the Cilium CLI will determine like what type of thing we're going to install into and pre-configure it. And if you wanted to take a look at what configuration might look like, you can do things like dry run -helm values. And this will not do an install, but it will show you what it determined about the world, right? So in this example, because we're using a kind cluster, what it's determined is that it will use IPAM mode Kubernetes. It will configure the operator to only run one replica because there's only one control plane node. It's determined to use routing mode tunnel, and the tunnel protocol will be VXLAN. Let's turn on some other stuff. This turns on Cilium Hubble. So as we watch here, we can see that things are coming up. We have Cilium installed. It's all running. We're just waiting for Hubble Relay to get pulled in here, which probably won't take too long. Probably already been done. Yeah. So now we're in a running state. We've got our cluster set up. Now, the other thing I didn't do was I didn't disable kubeproxy. I left kubeproxy running, right? Now, I'm going to show you like kind of an example of the IP tables churn that we were talking about before, because we're using Cilium, but we're also using kubeproxy, and kubeproxy does a lot with IP tables. So let's do docker exec ti kind worker bash. And what this does is it allows me into the kind worker so I can do things like IP tables save. And here we can see that already there are 107 rules that have been created. And this is just I mean, I haven't installed any applications. There are only just the default services running, etc. So there's already 100 rules. We haven't done much. And in these rules, you can kind of see kind of like what they're doing if you're looking at it, right? So here's the Hubble UI service. Here's the kubedns service. Here's the default Kubernetes HTTPS service. DNS metrics, Hubble Relay, Hubble Peer service, right? We can see the names of those things, and we can kind of see how this is implemented. So when you think about a Kubernetes service inside of Kubernetes, what you're doing is you're creating a mechanism by which an application can interact with another application, say your application interacting with a DNS server, right? When it does that, it doesn't interact with the actual pod IPs, it interacts with kubedns, and kubedns is exposed by a service. No, actually, let's do this, split horizontally. So kubekettle get SVC -n cube system. And we can see kubedns is right here, right? And if I were to start up a new container, just to show you what I mean by it's actually leveraging the service, if I do kubectl run it bash image equals bash, what this will do is it'll spin up a little bash image. And if I do cat etsy resolve.conf to see how DNS is configured, I can see that by default, when a new pod is created, it gets a name server of 10.96.0.10, and that IP address is the same IP address as the cluster IP address. So when we're interacting with DNS, we're actually making use of this service. And the way that kube proxy implements it, this is different than the way that Cilium implements it. Like you don't actually have to run kube proxy in your clusters if you don't want to. You can actually just use Cilium to do all of that work. But in our example, let's say we were going to use it. Kube proxy actually handles it this way, right? So when traffic is coming from the pod and traffic is leaving that pod and headed for the DNS servers, let's find the rule that catches that. And there we go. So if the traffic is coming with a destination of 10.96.0.10/32, and the protocol is TCP or UDP, actually I think there's a UDP rule somewhere else, but you get the idea. If it's coming in this way, this is actually matching on a different port, 9153, then send it to this other service. This is the one matching, there it is. So this is the one matching TCP on port 53. And this is the one matching UDP on port 53. Most applications use UDP to interact with DNS. And what we see in this rule set right here is we're saying if the traffic is destined for that, then we want to go ahead and forward it to this other function. Let's go take a look at this other function, which is kube service TCOU, which is right here. And that's saying if the source is 10.244.0.0.6, if the source is not 10.244.0.16, which is the actual CIDR for pods, so all of the pods should be within that range, and the destination is 10.96.0.10, then I want to go ahead and kubemark mask. But if the source is okay. And then we actually use this mechanism here to randomly forward the traffic across two pod IPs, 10.244.0.243 and 10.244.0.59. Right? And so in this example, this is actually how the service is going to be mapped, right? That traffic is going to go ahead and masquerade, and it's going to then go to one of these two based on a random statistic. Now, let's say we scale DNS up. What do you think will happen? Okay. Do you think kube proxy is going to use IPsets? Because if you do, you're wrong. Instead, we just see those other IP addresses showing up as new rules, which is what we were talking about before, right? So our old rule set was like 100. Our new rule set is 134. Let's scale it up to 10. 143. 179. All I did was add 10 hosts, and that's now 179 rules, 10 pods to a rule set, which is kind of wild when you think about it, right? Let's make a new deployment. kubectl create deployment echo image equals inanimate echo server replicas, but let's say 50 port 8080 expose. Whew. Now we're up to 332 rules. Why are there so many rules? Well, there's so many rules because every one of those IP addresses is part of, there we go, yeah. Every one of those IP addresses is part of a service. Isn't that wild? So you can see how this is the simplest of examples. You can see how this would get wild. Just kube proxy by itself, without doing anything else, would get pretty crazy with IP tables rules, right? What if I were actually using network policy, and network policy was implemented in IP tables? What would happen then, right? Hopefully, I mean, and I can tell you empirically that a lot of the things that are out there that actually use things that are doing things like enforcing network policy, leveraging IP tables, understand the value of IPset because it would greatly reduce the number of rules that we affect traffic for. Yeah, it's a drinking game, Stephen. No, I'm kidding. Some drinking games are just water drinking games. Yeah. Anyway, you get the idea. Kind of wild when you think about it. So let's jump into kind of like this pattern and how this pattern works, and let's talk about why you would want to do it. So let's say kubectl delete. Actually, you know what I'm curious about? Let's do this. Kubectl expose. Nope, I want to be over here. Kubectl expose deployment echo type node port name echo and b. Sure. It'll get svc. So I've exposed this guy on a node port 32182, and I did that by creating a new service, which of course means I have way more rules again. But you get the idea. And then actually that looks, yeah, it's about the same. So then I can do curl. Actually, I can do kubectl get nodes dash wide curl. Boop. Oh, whoa. Sorry about that. A little jumpy. All right, and then our port is, what is our port? 32182. There we go. And then what is the IP address? Where you're coming from? We're coming from 10.244.181. Oh, I see what happened. Okay. Ha, that's fun. Kubectl edit service. Echo no. External traffic policy local. 172.18.01. All right. So what I did there was I changed the service to make it so that it understood that I wanted to only connect to applications that were local to the nodes so that I could preserve my requesting IP address, which is the IP address on my host, which is associated with the Docker network. So here is the Docker network. You could all, actually, let's see, Docker network OS, IP2. Let's do IP adder. Whoop, whoop, whoop. Ding, 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 ding. All right. And then here, actually, Docker 0 is my bridge, or is my interface. And there's my 172.17.01 address. And that's actually what's showing up. Oh, sorry, I forgot. In kind, it creates its own bridge, which is the 172.18.01 network, which is the kind network, which is why there's one that's called kind. That's what that's about. All right. So that's all working. So now what I'm actually curious about is, can we figure out a way? That might actually just be enough. Let's play with this a bit and see how this is going to work. So next thing we're going to do is we're going to create a network policy. And to do that, let's go to network policy.io. If you haven't seen this webpage, it's a great webpage. It gives you examples of how to create network policy, not just for Kubernetes network policy, but also for Cilium network policy. And there's some great examples of the policy repo, like some examples of like how this would work. All that stuff is in here. So if what you want to learn about is network policy, this is a great starting point. And there are resources kind of talking through like how all of this works, including some things from Datadog talking about FedRAMP and the birth of network policy, kind of fun stuff. So let's do the network policy editor. Start. And I want to two-sider. So I'm going to allow 172.18.0, actually 17.0. Let's see if this actually works. Hold on. Before I do this, let's do, I think I know what I want to do here. I want to do an egress policy. I want to do Docker run it echo image equals inanimate echo server. Dash detach name echo Docker PS. Docker echo. I could, and then Docker inspect echo. And the IP address it has is 172.17.03. So from in here, curl 172.17.03.80. Don't have that. Okay, so I have to do IP table save. This will be fun because I'm basically going to open up the connections back and forth between two Docker bridges. Not something you may have seen before, but it's kind of necessary because I want to allow traffic to move back and forth between these networks. So let's go ahead and do that. Let's do sudo IP table save. So I want, and then my bridge, I think it's what is it? It's Docker network. IP adder. So what I want to do is I want to open up communication back and forth between, there we go, BR12E9 and Docker. So there's BR12E9 and there's Docker. And here's the isolation steps right here, actually, interestingly enough. So that's how they're isolated currently. What I want to do, though, is I want to allow that communication. And give me 1 second here. So what I'm going to do here is I'm going to add a step to the isolation stage that will allow me to accept traffic back and forth between these two bridges. So I'm going to do sudo iptables-t filter-i docker isolation stage 2-i, then docker -o, that creates a bridge name. -j accept. We got to do it 2 one-way routes. -o docker. Oh, it's Docker 0. Haha. Docker 0. Help you sudo iptable save. We can see we now have our allows in the isolation stage. Here we go, right here. Oh, there we go. Isolation stage 2. Traffic is coming into Docker, and the destination is going to the other bridge. Allow it. If the traffic is coming into the other bridge and it's going to Docker, allow it. And that way, if that happens before the drops, which means we should be good to go. So now, from in here, we should be able to do that. And we can. All right, good. So that's all working. So now the subnet that is going to be my destination subnet is going to be 172.17.0.0, and that's how we're going to do it. So let's go back to our rule set, 17.0.0/20. What is it? 16, I think. 16. And we're going to add ports 8080, add rule. Now, because we have actually added a rule that drops traffic, it means that all traffic not already allowed is going to be dropped. So let's get a little bit more creative here. We're going to do allow anything. We're going to allow to any pod. We're going to allow, definitely going to allow DNS. but we're going to drop all of the traffic. So here we go. This is what we were looking for. So now here is our Cilium network policy. Right, and this is an egress policy that is dropping traffic, or that is allowing traffic to CIDR set 172.17.00/16 on port 8080. It's going to allow traffic to all other endpoints. It's going to allow traffic to cluster, to allow for DNS traffic to work. We're going to allow all traffic. So there we go. So that's all pretty good, but it means that when that thing's trying to reach the outside world, it's not going to be able to do so. All traffic is dropped. Let's download this policy. Close. And then let's go ahead and take a look. Oh, you know what? I didn't actually match anything. All right, what did I want to match? Endpoint selector. Default. App equals bash. Save. So that takes care of that one. Bash. All right, now I'll download it again. There we go, bash.yaml. Love it. All right, so now what I got to do is I got to do kubectl create deployment bash image equals. Actually, let's do this. Let's do kubectl run bash image equals bash bash. Actually, sleep infinity. Dry run dash o yaml. So what this does, it gives me a way to create a pod, and then I can go ahead and edit that pod and create that pod. Let's do pod.yaml. Neat. Metadata labels. App equals bash. Sleep infinity. We'll ditch that. Okay, so now kubectl apply-f pod.yaml. Whoop. What did I miss? Name, spec, images, resources. Looks okay to me. What are we complaining about? Oh, I already created it. Let's go ahead and delete this deployment real quick. Delete pod bash. All right, there we go. Now kubectl apply bash dash f bash.yaml pod.yaml get pods dash l app equals bash. All right, so we have our bash running. Kubectl exec ti bash bash. Let's do that from over here. Exit kubectl exec ti dash n curl google.com. Git update. Curl minus L google.com. Whoop. All right. 172.17.03, I think it was, right? Port 8080. and it's working. Okay, so now the current access is from this pod, from this bash pod, I can actually access all of that stuff. And what I want to do next is I want to limit the access to that to something else, right? So if I do kubectl apply -f downloads bash.yaml, I'll describe Cilium network policy bash. So here is our Cilium network policy that we just created. We're still allowing 172.16, but because we have allowed that, we're not going to allow anything else. So let's do our curl again. Still works. What about IP of me? Nope. What about google.com? Nope. What about APK update? Not today. So this actually highlights two things. It highlights how to actually make a network policy that will make use of CIDRs and CIDR sets. It also shows how the enforcement works and how actually difficult it is to configure egress policy correctly. Because as you can see from within the pod here, depending on what I'm actually trying to access, things are pretty tough to access at the moment, which also again highlights how some of the things that you're trying to access, I mean, if you're going to write egress policy, you kind of need to know everything you're trying to access, at least by name, so that you can allow it. So let's go ahead and also explore this new feature. Now, I want to make sure I have time. I think I'm doing okay, but it's 11:55, so I have a few more minutes left. I wanted to explore one other thing, which is relatively new in Cilium, which is called a CIDR. Oh, actually, no, I don't have time. I'm out of time for today. But when I return, we will also talk a little bit more about this new feature. I will introduce you to it now. Explain. Let's say Cilium network policy spec dot ingress or egress to CIDR set. So here's the example and the language that describes what a CIDR set does. And then here you can see a new field. So the one we used was this CIDR field where we actually list the IP block that we want to only limit access to. But now we have this other new field, which is called CIDR group ref, which indicates a reference to a different list defined within the scope of things. And that new list is called kubectl explain Cilium CIDR group list. Nope. Kubectl API resources, grep list, CIDR. It is Cilium CIDR group. Am I spelling Cilium wrong? Oh, kubectl explain CCG. So here's our Cilium CIDR group. And then we can look at the spec, and we can see that the external CIDRs field there. So this is a list. This is a list of IP addresses or groups of IP addresses. And that's how that works, right? So with this feature, You can actually now create a list that you could reference from multiple network policies instead of having to actually put all of those IP addresses in one policy that you want to implement. You could actually implement the list and the policy separately from one another, which is mind-blowing. And that's actually really what I wanted to get to today. But I wanted to show you this new feature. We're going to be doing a little bit more of a little bit how it'll be a lab around it. But this allows you to define those external CIDRs that you actually want to implement in network policy and then reference them from your network policy instead of having to implement all of the IP addresses in the policy itself, which really allows for that disconnection of policy and CIDR lists, which is very similar to IPset, which is what we were talking about earlier. Anyway, thank you for tuning in. I hope this was educational. I know I ramble a bit, but I think it's pretty fun, and I hope you're into it as well. And I hope you have the best weekend of your life. I'll see you all later. Bye.